Okay, today we're starting chapter 4, and I am going to lecture on something called electron configuration. And it's kind of weird at first, and it's actually pretty easy. We just got to get some basics down. Okay, so on the basis of the work of Rutherford, which is the guy who discovered the nucleus, um, the fact that the electrons are in the cloud and they orbit the nucleus. They're just that the electrons take up most of the space and the nucleus takes up most of the mass. And then a guy by the name of Niels Bohr who figured out that the electrons are in the orbitals. Um, we have what became known as the planetary model of the atom. And basically, it said that an atom has a nucleus, which is very similar to our sun, and the electrons orbit the nucleus very much like the planets in the solar system orbit our sun. The difference is that the universe is much simpler because all of the orbits are the same shape, they're ellipses, and it's two-dimensional. So all of the planets are orbiting the sun in the same two-dimensional plane. What actually happens in a real atom, and so I'm going to come down here and I'm going to show you the pictures. These are the orbitals. There's four orbital types. There's an s orbital, and I think this designation comes from the fact that it's spherical, and the electrons orbit the nucleus. So you can think of the nucleus right in the center where this x, y, and z axes intersect. They orbit the nucleus at the speed of light, and if you traveled their path for a couple minutes, electrons traveling in an s orbital will carve out a spherical shaped orbital. It's actually a probability argument. It's 90% of the time, but s orbitals, this is the red one, they're spherical and it's three dimensionals. It's not like the planet, it just, speed of light or electromagnetic radiation is 186,000 miles per second, and it's orbiting the nucleus. And if you just trace the path for a couple minutes, it would carve out the spherical shape. But it's not like the solar system where all of the orbits are the same, because then some atoms travel in what are known as p orbitals. And there's two lobes. It kind of looks like a three-dimensional figure eight. It pinches right by the nucleus, and it's still an orbital. If you trace the path that the electrons travel for a couple minutes, it would, oh, all of a sudden this is bigger. It would carve out these shapes. These are the d orbitals. There's actually five of them. Um, this one has four lobes. 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 This looks like kind of like a p orbital with the hula hoop in the middle. In the middle, it actually has three lobes. This baby blue one, this baby blue one, and this blue one. And these are called d orbitals. So it's s, p, d, and f. And then these are the f orbitals, and these are really complicated because this f orbital looks to me like it has 1, 2, 3, 4, 5, 6, 7, 8 lobes. This one has 1, 2, 3, 4, 5, 6 lobes. This one has 1, 2, 3, 4, 5, 6. This has four lobes. Um, sphere on the top, sphere on the bottom, two hula hoops. This one, um, these are very complicated. It's even hard to, I think this have eight lobes. I think 1, 2, 3, 4, 5, 6, 7, 8. So what you need to know is that the electrons orbit the nucleus like the planets orbit the sun, except there's four different shaped orbitals that we know of. S, which is spherical, so like think a marble or a golf ball or a baseball. And then you have p orbitals, which are like two s orbitals pinched together. I say three-dimensional figure eight. These are d orbitals, and this is f orbitals. And the thing I want you to see is as you go, the least complicated is s. There's one lobe, I call it. These p orbitals have two lobes. they're getting more lobes and more complicated. D, this has 4 lobes, this has 4 lobes, this has 3 lobes, this has 4 lobes, this has 4 lobes. And then when you get to F orbitals, they have 7 or 8 lobes, most of them, except for this weird one. The other thing is there's a pattern. It goes 1, 3, 5, 7. Each of these orbitals can hold 2, so s orbitals can hold 2, p orbitals can hold 2 plus 2 plus 2 or 6. D orbitals can hold 2 plus 2 plus 2 plus 2 plus 2 or 10, and F orbitals can hold 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2 or 14. Okay, I can't even imagine how stupid that sounds. So then this is called the diagonal rule. This is the diagonal rule. Notice that you have 1, 2, 3, 4, 5, 6, 7 rows and 4 columns, the S column, the P column, the D column, and the F column. I have this run off for you. I don't have it written on here, but I will. By the way, not coincidentally, the modern periodic table has 1, 2, 3, 4, 5, 6, 7 rows. 1, 2, 3, 4, 5, 6, 7 rows. And I don't actually have this on there, but s orbitals hold 2, p orbitals hold 6, d orbitals hold 10, and f orbitals hold 14. 2, 6, 10, 14. Again, not coincidentally, this is S, 1, 2, this right here, this is 6, this is 10, and these bottoms are 14. And we're going to talk about all of that, that the modern periodic table is arranged according to electron configuration. So I'm going to go here and I'm going to open up a new slide. I'm going to generate this. You do not have to generate this. So we go 1s and then 2s, 2p, and then 3s, 3p, 3d. This is what I want you to notice. This is the first row. This is the second row. This is the third row. This is the S column. This is the P column. This is the D column. And then we have 4s, 4p, 4d, 4f. So 1, 2, 3, 4, and then it goes 4, 3, 2. Don't ask me what, well, this is all we know so far. You don't have to do this because I've run it off for you, but this is what I had to do in grad school. I would just generate this 1, 2, 3, 4, 4, 3, 2. Notice I'm very careful. I put the S's in one column, the P's in one column, the D's in one column, and the F's in one column. And again, I'd like to go back down here to this. There's 4 shapes of orbitals. S is spherical, P is 3-dimensional figure 8, D are complicated. Most of them look like 3-dimensional 4-leaf clovers, except for this one. And F's are so complicated, I can't even tell you what they look like. Just know that as you go down, they have more lobes. They can hold more electrons. So S orbitals can hold 2, because each of these pictures can hold 2. So S, 2, P, 2 plus 2 plus 2. 2 go into this P, 2 goes into this P, 2 goes into this P, and then that's 6. We'll do more of this. Okay, so here's the diagonal rule. This is very weird. I'm going to switch colors. The 1s orbital fills first. When you get to the end of an arrowhead, you jump up. Then 2s, then 2p and 3s, then 3p and 4s, then 3d, 4p, 5s, then 4d, 5p, 6s, then 4f, 5d, 6p, P7S, and then 4F65P. And this is what you got to know. S orbitals can hold a max of 2. P orbitals can hold a max of 6. D orbitals can hold a max of 10. And F orbitals can hold a max of 14. And if you can see the pattern, 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14. We think we might find a g orbital someday, and it will hold 18 electrons. Now, this, what I just drew, looks like this that I gave you, 1s. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So it's interesting. It's complicated because if I was chemistry queen of the universe, the first energy level would fill, then the second, then the third. But here's what actually happens. If you follow this out, the first energy, 1s fills first, and then 2s fills second, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, 4p, 5s, and then I jump down here, 4d, 5p, 6s, and then 4f, 5d, 6p, 7s. So 4f, uh, 5d, 6p, 7s, and then 4f, 5d, 7p, 4f, 6d, 7p. They don't fill in order. How come it isn't 1s, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f? That's not how they fill because, going back to the thing, um, they fill low to high energy. And so this is the order they fill in. So you have to do this. You'll see me flip back and forth now between these two as I'm going to flip back and forth between this as I do this. Now, um, just to be sure I'm still taping good. Here's my first example. This is crazy. I want you to do the electron configuration for aluminum. Okay, so this is what you do. You first go to the periodic table and you find aluminum. It's right here. Aluminum is atomic number 13. That means it has 13 protons and 13 electrons. So I'm going to come over here. Aluminum is atomic number 13. So I have to aluminum has 13 electrons orbiting the nucleus of the atom, and the electron configuration gives you like the address of where the electrons will be. So, and by the way, this is confusing the first day. It takes a couple days for it all to come together. So, here we go. According to the diagonal rule, the 1s orbital fills first. So what you do is you write 1s, because that's the first orbital that fills. And then s orbitals hold a maximum of 2, and so the notation is 2. This means there are 2 electrons orbiting the nucleus in a 1s-shaped orbital. Now, aluminum has 13 electrons. You have placed 2 of them. 13 minus 2 is 11. You have 11 left. Now, get to the arrowhead. Then what fills? 2s. Okay, the next orbital that fills is 2s. S orbitals can hold a maximum of 2. 11 is bigger than 2, so 2 come out. 11 minus 2 is 9. Aluminum has 13 electrons. We know the address or where 4 of them are. Now we need to place the next 9. Then you go back here. What fills after 2s? 2p. But now this is interesting. P orbitals can hold a maximum of 6 electrons because 9 is bigger than 6. They all go in here. 9 minus 6 is 3. Aluminum is 13 electrons. 2 plus 2 plus 6. We've placed 10 of them. We have 3 left. Now, what fills after 2p? It looks like 3s. S orbitals hold a maximum of 2 because 3 is bigger than 2. They all go in here. 3 minus 2 is 1. And now here's the interesting part. What fills after 3s? Well, you jump up here. It's 3p. Now, p orbitals can hold a maximum of 6. But okay, so if they can hold 6, it can hold 1 or 2 or 3 or 4 or 5 also. And maximum of 6. You only have 1 electron left. And so it ends in 3p1. And so one of the things you'll know, this is the electron configuration, this whole thing. And what it means is aluminum has 13 electrons. 2 are orbiting the nucleus in a 1s. 2 are orbiting the nucleus in a 2s. 6 are orbiting a nucleus in a 2p shape, 2 are in a 3s, and 1 is in a 3p. The other thing is, what's the difference between a 1s, a 2s, and a 3s? A 1s is like a BB, a 2s is like a marble, a 3s is like a golf ball. They're all spherical shaped. 1s has a shorter radius than a 2s. What's the difference between a 2p and a 3p? Well, this would be a 2p. This would be a 3p. Just a little bigger shape thing. Okay, let's do another one. I'm going to do 5 of these really fast. And what if I ask you to do the electron configuration for, let's do copper. No, let's not do copper. Yeah, let's do copper. All right, so we're going to go here. I'm going to go back to my periodic table, and I'm going to find copper. It's right here. Copper, Cu, copper. Copper has 29 electrons. The electron configuration tells me where those 29 electrons can be found in the atom. It's kind of like giving the address. So, okay, so now remember, copper has 29 electrons. Okay, which orbital fills first? I'm going to go a little bit faster and go back to the diagonal rule. 1s fills first. S orbitals hold 2 electrons. So here we go. What fills first? 1s. S orbitals hold a maximum of 2. 29 is bigger than 2. Now we're down to 27. Okay. Now what fills after 1s? 2s. So 2s fills. S orbitals hold a maximum of 2. 27 is bigger than 2, so it holds the maximum. 27 minus 2 is 25. To be perfectly honest, by the time you guys take the test, most of you are counting on your calculator. Hit the arrowhead, jump up. What fills next is 2p. But this is interesting. P orbitals don't hold 2, they hold 6. So 25 minus 6 is 19. So copper has 29 electrons. We've placed 10 of them because 2 plus 2 plus 6 is 10. We have 19 left. Now, what fills after 2p? Well, look, what fills after 2p? 3s. However, s orbitals hold 2. 19 minus 2 is 17. Okay, back here, what fills after 3s? Well, when you hit the arrow, you jump up 3p. But p orbitals hold what? A maximum of 6. Uh, 17 minus 6 is 11. We have 11 left to place. Back here, what fills after 3p? Just follow the yellow brick road or follow the diagonal, 4s. S orbitals hold a maximum of 2. 11 minus 2 is 9. And now life gets interesting. Why? Because what fills after 4s? 3d. Now this is the first time that a d orbital's come up. D orbitals can hold a maximum of 10. Remember, s's hold 2, p's hold 6, d's hold 10, and f's hold 14. Now, d orbitals can hold a maximum of 10, but we don't have 10 left. We only have 9 left. And so this is the electron configuration for copper. And notice, I'm going to switch colors. I want you to notice that 3s fills, then 3p, but then not 3d. 4s fills before 3d, and that's why you need the diagonal rule. They don't fill. It would be much easier if all the 1s filled, and then all the 2s filled, and then all the 3s filled, and then all the 4s filled, but that's not what happens. If you remember when I was doing this, it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. It's very confusing. That's why you need that. Okay, now let's do another one. I want you to get enough. So let's do the electron configuration for, let's do iodine. This is a fairly complicated one. And then I'll do one with the f orbital, and then we'll be done. Okay, so I go back here, and I find my periodic table, and I find iodine, and iodine is atomic number 53, which means that iodine has 53 electrons, and we have to place them all. It's a pain in the butt, but let's do it. 53. Remember, the an iodine atom has 53 protons, 53 electrons. We're doing electron configuration, so we only care about electrons. All right, here we go, back and forth. I'm going to go back and forth between this. What fills first? 1s. S orbitals hold 2. 53 minus 2 is 51. Okay, back here, What fills after 1s? 2s. S orbitals hold 2. All 1s, 2s, 3s, 4s, 5s, 6s, 7s, all of them hold 2. 51 minus 2 is 49. Um, Back here, 1s fills, then 2s, then 2p, and 3s. So 2p fills, p orbitals hold 6. 49 minus 6 is 43. Then the 3s fills, but any s orbitals hold 2. 43 minus 2 is 41. Now, so 1s, 2s, 2p, 3s, then it looks like 3p, 4s. So 3p, any p orbitals hold 6. 41 minus 6 is 35. And then what fills after 3p is 4s. Oops, that's not what I wanted to do. I've been recording for 20 minutes. So then 4s fills, and then 35 minus 2 is 33. And then, okay, so we've got, of the 53 electrons, we've placed 20 of them, because 2 plus 2 plus 6 is 10, 12, 18, 20. Now, what fills after 4s? Well, you jump up and it's 3d, but thank God d orbitals can hold 10, so so then what fills now is 3d. 33 is bigger than 10, so it fills to the top. 33 minus 10 is 23. Now, what fills after 3D? 4P. Oops, wrong one again. What fills 4P, but P orbitals hold 6. 23 minus 6 is 17. What fills after 4P? What fills after 4P is 5S. S orbitals hold a maximum of 2. 17 minus 2 is 15. Okay, now back to this. It's hard to go back and forth. You won't have to. Okay, I forgot where I was. What filled is 5s, so now I got to see what fills after 5s. What fills after 5s? If you look here, you jump up, it's 4d, then 5p, then 6s. Patterns on the column: 4, 5, 6, 4, 5, 6, 7, 5, 6, 7. So what fills after 5s? 4d. So then 4d, but d orbitals hold a maximum of 10. 15 minus 10 is 5. And then when I go back here, what fills after 4d is 5p. Now p orbitals hold a maximum of 6, but we only have 5 left, so it ends in 5p5, and this big, long, giant thing is the electron configuration for iodine. It tells you 2 electrons are in a 1s orbital, 2 are in a 2s, 6 are in a 2p, 2 are in a 3s, 6 are in a 3p, 2 are in a 4s, 10 are in a 3d, so it's kind of like an algebra. Now, the last thing I want to do, I know it's taken a long time, but we need to do in row 6 or 7, because this, we need to get, you haven't seen any with the f orbital. So I'm going to do 107 just to be obnoxious. This is named after Niels Bohr. This is borium, B-O. He is the guy that discovered that the electrons travel in the orbitals, the s, the p, the d, and the f orbitals. And so I would like to do, my last one is borium. Borium is atomic number 107. This one is going to take a long time. Borium is 107, okay? That's not the one I want. I need the diagonal rule. Okay, 1s fills first. 1s to 107 minus 2 is 105. Okay, then what fills after 1s? It looks like 2s. 2s, s orbitals hold 2. We're down to 103. Going faster now. What fills after 2s? 2p. 2p, but p orbitals hold 6. 103 minus 6 is 97. Okay, then what fills after 2p? 3s. S orbitals hold 2 because they're simple. Now I'm down to 95. What fills after 3s? 3p, because from 3s you jump up to 3p. But p orbitals hold 6. 95 minus 6 is 89. Over here, what fills after 3p? 4s. For S2, I'm down to 87. What fills after 4s? 3d. I love d orbitals because they get rid of a lot. 3d10, down to 77. Um, what fills after 3d is 4p, but p orbitals hold 6. 77 minus 6 is 71. Um, what fills after 4p? 5s. S orbitals hold 2. 71 minus 2 is 69. I'm going to actually come up here with the 69. Let me grab the eraser um, so I don't lose track of where I am. Okay, so now we just finished filling 5s. What fills after 5s? You jump up here, it's 4d, but d orbitals hold 10. 69 minus 10 is 59. Um, what fills after 4d? It looks like 5p, but p orbitals hold 6. Uh, 59 minus 6 is 53. What fills after 5p? It looks like 6s. I got to come around here. 6s2, I'm down to 51. It's taking forever, but it's not hard. What fills after 6f? Thank God, 4f. It's the first time you've had a 4f. 4f. F orbitals hold 14. I can't even do this. 11 minus 4 is 7. 4 minus 1 is 37. I went from 51 to 37 with that F orbital. Okay, so now I'm down to 37. I'm getting close. What fills after 4s is 5d, but d orbitals hold 10. So now I'm down to 27. What fills after 5d is 6p, but p orbitals hold 6. So now I'm down to 21. What fills after 6p is 7s. S orbitals hold 2. I'm down to 19. Life is getting interesting. What fills after 7s? 5f. But f orbitals hold 14, and 19 is bigger than 14. So 19 minus 14 is 5. And then what fills after for 5f is 6d. D orbitals hold a maximum of 10, but we only have 5 left. And so this whole big, giant, long thing is the electron configuration for borium. Oops, I gotta go right here. All right, cool. That's it. You guys will have an assignment. You're going to do 10 of these. Some of them are really short. Um, some of them are more complicated, and it will be due tomorrow.